Thank you, Juliet. So just as Juliet said, there's a bunch of people that are involved in this. From the USGS, you can see here we have listed Patrick Barnard as the principal investigator, myself, Lee Erikson, director of modeling, Juliet, who you just met. Amy Foxgrover is our GIS person, and we have assistants from Lee Herdman and Patrick Limber, who is here with us in the audience and who will be answering questions, and he does bluff recession modeling. Long-term, Andy O'Neill is our everyday now cruncher of the model, overseeing the running of it, continuing of it. Sean Vitusik is the shoreline change, long-term shoreline change, and Jonathan Warwick we have for hydrology. And if to contact any of us, it's our first letter of our first name and then last name at usgs.gov. So that's how you can reach us. And so I wanted to, of course, acknowledge all the collaborators and the funders. There's many of them, as you can see, and we're very appreciative, that you're here today and have the interest. We hope this is a useful product. So I was going to give an overview of Cosmos and what's under the hood. The Cosmos is not a model per se. It's a system of models that we use. So we call it the Coastal Storm Modeling System. It's a physics-based numerical modeling system for assessing hazards. We started in Southern California, where we are now. We started with this back in 2011, where we looked at first-order estimates, and we applied two sea level rise scenarios, and I'll go over that a little bit. That's where we started in 2011. Since then, we didn't do climate change back then. Then we moved to the central north coast outside of San Francisco, and that's when we added in the climate change component. Since then, we've gone into San Francisco Bay, we've gone north of San Francisco, and now we're back down here in Southern California, and we're continuing the work for the remainder of the California coast. Cosmos 1.0, as we call it, which was the one back in 2011, our first go at this, has an outer coast focus. It did not go into the bays and the lagoons. The flooding is based on the maximum wave run-up, which is, so we didn't go into the details of the actual overland flow on that. And there was a limited set of scenarios for that. We used the arc storm, which is a hindcast of one of the larger storms, basically an 1863 event that was put together. And we also simulated January 2010 storm with 2 sea level rises. Those data are available. But to model vulnerabilities with climate change, we needed to go one step further, and that's where we are now with Cosmos 3.0. And for that, we've added a bunch of scenarios. So we have 40 plausible future scenarios going from 0 to 5 meters in sea level rise and 3 different storms, projected storms for climate change and background conditions. And for that, we use downscaled waves, winds, first of all, that are downscaled from the Scripps Institution of Oceanography that we apply to the nearshore region. We use downscaled waves from a global climate model, and that's also from the global climate modeled winds that we apply. We have long-term coastal evolution in there. We have discharge from rivers for event response. Vertical land motion is factored into the uncertainty. And we also now are employing the web-based tool, which Michael will present after me here. So a little bit overview of Numerical Modeling 101, kind of what's the 2 components that are involved. We have coastal area models. So if you can see here, 3-dimensional models. So then you're really getting down into the gritty-nitty and all 3 dimensions in our space. This is usually used for sediment transport, but it's very, very computationally intensive. It takes a long time to run. Many times we do vertically averaged 2DH, we call it. So in this case, we average in the vertical, but we have a resolution in the XY space, right? So like a map. And this is usually sufficient for waves and currents, and that's what we use in our modeling system. Thirdly, there's coastal profile models, and coastal profile models are across shore transect, across the beach. So we call those 2D because you have X and Z, so you've got going across the beach and then going up. These are much quicker to run. We're talking for these, for long-term simulations, months to run these, whereas the cross-shore models are much quicker, and that's why we combine the two. So for the Cosmo system, as I mentioned, we go from the global to the regional to the local scale. On the global, we have the downscaling to the waves. On a global scale, we bring it down to the west coast of the US, and we pick those out. We bring that into the regional models, which is a coupled system of Delft 3D, Flow, and Swan. We also include here the Scripps Institution of Oceanography downscaled winds to apply that so that we get the local effects of local wave growth. And then because of computational limitations again, we have yet another system of local, and here we have many smaller grids that provide overland flow and better resolve the processes in bays and lagoons. And for the outer coast part, we bring in the X-Beach, the cross-shore model that we were talking about. And for the cross-shore models, this is where we bring in the long-term cliff recession as well. So in these components, for these models, we account for many of the, if not all of the major relevant processes that contribute to the total water level at the shore and the flooding. We have sea level rise, obviously, tides, the astronomic tides, the regular changes in water levels due to planetary motion, sea level anomalies, those associated with larger scale Pacific Basin like El Nino, waves. Waves are breaking at the shore and causing the run-up. Storm surge, the rise in water level due to persistent winds and sea level pressures. And also river discharge, so where the river meets the incoming ocean water and the confluence of that going up. And the picture on the top is an illustration of the importance of the underlying elevation model that you have, the digital elevation model. So you can see here, in this case, this is the same conditions that's coming from offshore, but you have a much milder beach here, and it can actually run up further. It can go up further and wet this house. Whereas if you have a very steep shore, it crashes, it breaks further off, and it, whoops, sorry, and it doesn't make it as far upshore. To emphasize, what I just wanted to emphasize here is that by including the sea level anomalies, waves, and storm surge, we add, it does make a difference as opposed to just looking at sea level rise. So in this image here, you can see that the blue is 2 meter sea level rise scenario with no storm versus the yellow, you see the edges are expanded because of the storm that we're accounting for. So overall, yes, we're doing 40 scenarios. We have these components that I just talked about, the Pacific Ocean waves, the storm surge, the fluvial discharges, sea level anomalies, the astronomic tides. And all of these are used to force the model with different sea level rise states, going from 0 to 5 meters. From 0 to 2 is 25 centimeter increments. And then also for these individual storm events. And those are the future storm events. For those storm events, we have to account for the variations along the coast. Specifically in the Southern California bight here, there's the orientation of our shore makes it such that the 100-year storm is not necessarily the same event up here or up here. It's hard to tell. I'm sorry on this. This color scaling is not great. But what the main point here is, what we did was we went through and calculated estimated total water levels time series for all these individual points along the whole coast, and then looked at those total water levels to see what storm caused the 20-year, the 1-year, and the 100-year event. And what came out is that almost one single storm, Storm 1, accounted for 95% of the area, and 3 and 2% of these other two storms. When you go down into the less intense storm intensity, so the 20-year here, for example, you see that Storm 1 only affects 40% of the area. Storm 2, which is slightly different direction, incidence, wave direction, and wind direction, is about 30%. So we have to account for different storms coming and approaching. Yeah. For the fluvial discharges, these are the discharges that we've been including in our model simulations, and we attempt to project what the discharge might be with that associated future coastal storm. And we have a system set up where we look at the sea level pressure gradients and correlations between past events, and then we bring those into the future. And I can talk about that separately with people who might be interested, but it's a little more involved. As you can see, this is for San Diego County, and we're covering most of all the gauged rivers that are within the San Diego County here. For long-term morphodynamic change, we're looking at 100 years of shoreline change for more than 4,800 cross-shore transects, those 2D transects. And we're considering all kinds of shores, the sandy beach backed by sand berms or dunes, sandy beach backed by shore protection structures, which there are a lot of, erodible coastal bluffs. So those include then a long-term shoreline change component. For tidal flats and wetlands, we did not do any change. We did not say that there was any accretion or deflation, for that matter, in any of the wetlands for these simulations. We decided to leave them as they are. Long-term morphodynamic change in sandy beaches. This is a numerical model that was developed as part of this project. It solves the conservation of sediment mobilized by waves and sea level rise. It has I should actually say 4 components. It has the longshore. So you can see with the red, the cross-shore component and sediment supply by natural and anthropogenic sources. And the way that this is put together is a synthesis of previously published models and the improvements to those that have been made. We also have long-term morphodynamic change for cliffs and bluffs. And what you see here is a cross-section of a cliff toe, cliff edge, got the beach, and so what happens here was that when this erodes, the material falls here and protects the beach from further attack. This is also a numerical model that has been developed as part of this effort. It uses an ensemble of up to 7 cliff retreat models per transect, similar approach as to the long-term shoreline change. It's synthesized from the scientific literature, and again, from these 2D and 1D models, and it's been improved upon and has an artificial neural network. And also, Pat is here to answer more detailed questions about that as well. So incorporating the long-term change into this system of the Cosmos modeling system, this is a regraph of almost the first slide, where we have global scale. We start with the global scale, then we go to the regional scale, which we call Tier 1. We bring that down into Tier 2, and then into Tier 3, which is the X-beach, the cross-shore. This is where we add the long-term shoreline change component into the X-beach models that are run. We then bring this together, the local scale Tier 2, which are the flood maps, overland flow, and we bring that together with our cross-shore model, and we have to merge those to make a flood hazard maps, to make the final flood hazard maps. So merging those, this is what saying here, that this is the high resolution for grids and harbors. There's a grid here, but it's hard to see on the screen. So this is water levels that are produced by one of the model simulations. Tier 3, as we call it, with the X-beach open coast. These are the transects. We get results for these transects. We interpolate across them, and then we add these two together to make one water level flood map. This is a digital elevation model. We then subtract from the water levels to get the final combined flood map. Some of the results, which are actually on the posters here, these are pretty much the same thing. The point here, I'm just going to flip through 3 of them real quick because the posters are there and we can talk about that later. But here you can see the difference in the no storm condition with all the different sea level rise and with the 100-year projected storm condition. There's, you see, for example, 50 centimeters. We predict that, or project, I should say, that with the 100-year flooding of the Del Mar racetrack, if you add both the storm and the sea level rise, and that where you don't have it otherwise. Also for the city of San Diego, similar effects. The storm, Imperial Beach. So what outputs are available from these models? We have the long-term change for cliff recession and Sandy Beach. There are 4 coastal management scenarios, and those are all available on the web as well. For the flood modeling, this flood depths, extents, low-lying vulnerable areas, including integration of the long-term morphodynamic change, maximum water levels, flood duration, maximum wave height, maximum velocities, maximum wave run-up, and we also include the uncertainties that we obtain from the model and the DEM as well. And that's for each of the 40 scenarios. So the coastal storm modeling system that I just went over, this data is presently also available at here, this link, in Google Earth KMZ as reshaped files. Or there's also a document that we're preparing that is in review currently that talks about these methods in more detail. And that will be available, I would think, in about a month or so, maybe 2. So the data here for the Cosmos modeling system is fed into OCOF, our CoStar Future, which is then the web tool that you can access and easily visualize and download data and compare data sets. And this is Michael will talk about this. Yes? To go on to that. All right.